Okay. Good morning, everyone. Uh, Thank you for joining us today. I hope to enjoy my presentation. So without any hesitation, let's start. The title of my presentation is on machine learning-based surrogate modeling of soil structure interaction problems. In this presentation, we have 5 chapters. We start with the introduction and what are the motivations. Then in 3 chapters, I present the works I have done during my Ph.D. And in the final chapter, I will present the conclusions. In the field of earthquake engineering, we are usually facing a problem like this one. We have a source of excitation which is located usually far from the localized feature we have. And these localized features can be either a building or a structure embedded in the soil, or even a geological inhomogeneity like a basin. And studying the wave propagation due to these localized features is called site response analysis. And this is one of the main topics in this presentation, and we are going to talk about that a lot. Usually, instead of modeling such a big problem, we transform the original problem into a smaller problem with a smaller domains, and we use the finite element method for the purpose of site response analysis. And domain reduction method is one of the approaches we can use for this transformation from this big problem to this small problem. Also, domain reduction method is accelerating the modeling, but still considering a finite element model for the purpose of uncertainty quantification is expensive. For example, in one of my studies, I had a structure. I had 15 random variables in my structure, and I wanted to do the uncertainty quantification for this problem. And for that purpose, I had to run 42,000 simulations. And as you can imagine, running those 42,000 simulations took almost 1 year of my time. So it was pretty expensive. So we need to substitute the expensive finite element model with the surrogate model. Among the available options we have for the surrogate model, we chose to work with machine learning, and that's the topic of this presentation. One can divide the available machine learning approaches into 2 groups. The first group is data-driven models. In this model, we have access to the labeled data input-output pairs, and the way we define our losses is the difference between the predictions of this network and the ground truth observation we have as the labeled data. And depending on what is the structure of the data, we have different approaches. The second group, on the other hand, doesn't use any labeled data. They use the physical information, and they use those partial differential equation and physical log constraints as to define the loss functions. This approach has attracted lots of attentions recently in the field of engineering and mathematics. So let's start what we are going to see in this presentation. As I said, we are interested in performing site response analysis in different projects. And in each project, we are going to use a specific machine learning model. For the first project, we use data-driven model, and we try to solve the uncertainty quantification for a tunnel structure. For the second project, we are going to switch to PIN, and we start with modeling the wave propagation in 1D soil columns. And then we extend this project to 2D problem, and we are interested in solving the remote excitations by the pins. So because I'm going to mention domain reduction method a lot in the future slides, let's see what is the domain reduction method and how this method is working. Domain reduction method was proposed by Bielak in 2003. They said that this is the schematic figure of what we have as the original problem. We have some localized inhomogeneities, and we have some source of excitations far from these localized features. They decomposed that problem into two regions, the interior part and the exterior part, and they wrote the finite element equations for each of these regions. And they used an auxiliary problem where there is no sign of localized feature in this problem, in this system. And everything is based on the free field responses that we have, because there is no scattering wave in this problem. And again, they decompose that into two problems, and they write the equation for the exterior part, and they could write the effect of external source of excitation in terms of free field responses. The problem is that I have to escape here. That's really good at that. Is that working? Okay, so we noticed that they can present the effect of source of excitation in terms of the free field responses. So after that, by knowing the fact that the total response is the summation of the free field responses and the scattered waves, they wrote the governing equation for the entire system, but for the exterior part, they only considered the scattered components. And to eliminate the effect of this source of excitation, they plugged in the equation they had for the backend problem based on the free field. So as we see in the transformed problem, there is no effect of source of excitation, but we have two layers of the nodal loads, and which these two layers are next to each other, and they are very close to the localized feature we have, so we can solve this transformed problem. So with that in mind, let's start our first project and see what is the problem statement. As I said earlier, we have a tunnel structure subjected to the incident waves hitting the structure by the angle of theta. For the finite element model, we are going to use domain reduction method, and we are interested in predicting the horizontal and vertical response of 20 points located on the cross section of this tunnel. And for the sources of uncertainties, we have the earthquake data as our time series random variable, and we have some scalar random variables such as the angle of incident wave and the mechanical properties of the soil. Of course, there are there are a few ways that we can use to reduce the cost of uncertainty quantification for the purpose of soil structure interaction. One of them, for example, is reduced order modeling, which tries to reduce the fidelity of the problem. But as I mentioned earlier, we are interested in checking the performance of the machine learning approaches. So among all the available papers, this paper attracted our attention. They proposed a new variation of the LSTM model, and they called it LSTMS. They said that for the input and the output, we are going to divide these input time series into S number of stacks. And in each stack, we have a few data. For the input, they consider the full data, but for the output, they consider only the last data of each stack. So they have the problem of downsampling. And actually, what they are doing is just trying to reshape the structure of the input and output. So we proposed our modified LSTM model on top of LSTMS to enhance its performance by adding some features. The first feature is that we try to avoid doing downsampling. We try to avoid downsampling by considering the full stacks in the output. And the second feature was that we try to consider both time-dependent and scalar random variables as our inputs for the LSTM model. And the third one was that we wanted to train our model with easy to generate synthetic data with short durations. So this figure shows the LSTM cell for us. What is the content of the LSTM model? As we see, LSTM has 3 gates. The first one is the forget gate that forgets irrelevant information. The second gate is input that adds the new information. And the third gate is the output gate that passes the information to the next time step. And in this figure, we are showing that how these gates are connected to each other and how they pass information to each other. So we started tuning our LSTM model. The first tunable hyperparameter was the architecture of the model. We tried different architectures with different with different widths and depths. And we noticed that the cheapest architecture that can provide us with more than 95% confidence level for 10% error is 2 LSTM layer followed by 2 dense layers, where in each layer we have 200 cells. The second tunable hyperparameter was the number of samples we need for the training purpose. So for that purpose, we tried 5 different cases of having 10, 20, 30, 40, and 50 samples. And we noticed that having 10 and 20 samples leads to overfitting problem, but having 30, 40, and 50 samples are good. So we chose 30 samples as it was the cheapest one. And for the last tunable hyperparameter of our model was we checked lengths of the duration of the synthetic motions that we need. So we tried different durations, and we noticed with different number of stacks, and we noticed that having only 1 second of synthetic motion can provide us with more than 95% confidence level for 10% error. So to summarize, I said that our model is going to be trained with 30 samples. So what we did was using LHS model to generate 30 samples for our scalar random variables. On the other hand, we used 30 white noises. And now we can use this information and use our finite element model to get the output data. And after we have these pairs of input and output data, we can start training our model. And after that, we can test for as many samples as we want. The first test set that we considered for this project was white noises with different durations. We considered 50 white noises as the test set, and the duration of these white noises could be between 20 seconds up to 50 seconds. And we noticed that the majority of the responses have good accuracy. Their accuracy is more than 90%, but there are still some cases that their performance is poor. And when we plot these cases, we see that actually LSTM is capturing the trend of the responses, but because the amplitude amplitude of the responses are very small in comparison to the majority of the responses, our LSTM model is over predicting these cases. For the second test set, we consider 14 earthquake data with different PGAs, different duration, and different dominant frequencies. And for this case, we consider a more complicated system where the VS profile changes in depth based on this equation. And in this equation, VS naught, K, and N are our new scalar random variables that are going to be added. In addition to that, the burial depth of the structure is also a new random variable, but the quantities of interest are the same as the previous case. For this case, again, we noticed that the majority of the responses are good. And when we plotted the whisker box plot for different amplitudes, we noticed that all these cases that have poor performance, they belong to the responses that have less than 5 millimeter amplitudes. And they are very few, their numbers are very few. So it was time for us to consider our model as a forward model, our LSTM model as a forward model for the purpose of uncertainty quantification. And we said that we are interested in computing the racking displacement of the structure we have. To our surprise, we noticed that although our model is good in predicting the corner displacements, but when we subtract them from each other, the racking displacement is very bad. So at that time, we suggested that we should change our quantity of our interest and predict the racking displacement directly as the output of the surrogate model. And we noticed that in that case, we can predict the responses very well. In this figure, I'm showing that if we have 30 finite element samples, definitely we cannot capture the distribution of the racking displacement. But if we use these 30 finite element samples and train our surrogate model, our LSTM model, we can predict those 1,000, the distribution of 1,000 finite element samples. In this table, I'm comparing the cost of these different scenarios. If we train our LSTM model with 30 samples and predict the 1,000 samples, it's almost more than 200 times faster than running 1,000 finite element model.